A question that came up in the context of using a Q function and the z-score is why can't we treat the binomial, the normal distribution, as the exact probability of events that we're interested in? And the reason is basically that the exact probabilities are calculatable only using the binomial distribution, and the normal distribution is just an approximation. But more specifically, I'd like to explain why can't the normal distribution ever be actually equal to the binomial distribution. Okay, so let's imagine that we have this axis k indicates the outcome of binomial experiment. Let's say throwing a coin, tossing a coin 6 times and seeing how many heads we have. And so what we get from the binomial distribution is the probability that the outcome is each one of the integer numbers. Okay, so let's say this is the probability of 0, this is the probability of 1, this is the probability of 2, this is the probability of 3, and 4, and 5, and 6. Okay, so note that this is a probability that assigns a non-zero, this is a distribution that assigns non-zero probability only to the integers. Numbers that are not integer have probability 0. On the other hand, if we look at the normal distribution approximation, then what we have is something that maybe looks like this. Okay, so so unlike the binomial distribution, that is these are point mass functions, then the normal distribution is density. Okay, and therefore the density, the normal distribution, assigns probability exactly 0 to each one of the integers, and the probability mass function, the binomial distribution, assigns probability 0 to anything that maybe looks like this. Okay, so if you have a segment that doesn't include any integers, then the density assigns to it non-zero probability, but the point mass function will assign to it probability 0. So in that sense, they can never be even close. But there is another sense in which they are close, and that's when instead of using point mass function and probability density function, instead of using those, we use the cumulative distribution function, so the CDF, and in that case what we get is that for the binomial distribution we get something that looks like this. Okay, and for the normal distribution we get something that looks like this. Okay, so now if we can measure the distance, the difference between these two functions at any point we choose. For instance, let's say here, the difference is small, and also here the difference is small. Basically we get that for any value of z, whether it corresponds to an integer or not, the approximation using the normal distribution is a good one. That's it.